All right, good morning. Um, so this is where we stopped the last time, the law of mass action, and I think we kind of like already discussed this slide. But before I continue, I want to quickly apologize for having to cancel our last class at the last minute because of course it wasn't something I wanted to do, but I didn't have a choice. We had something an important departmental assignment that clashed with this class. So I didn't have a choice. We had to cancel the class. My apologies to everyone. Now, okay, so we were on the law of mass action, and we already said that for the formula is equal to activity coefficient is equal to uh the active mass is equal to concentration multiplied by activity coefficient. And we also said that for reaction involving gases and solutions, your activity coefficient is equal to 1, meaning that for such reactions, your activity coefficient is the same thing as your concentration. Now look at this kind of reversible reaction. Now, according to law of mass action, the rate of forward reaction, which you can take to be RF, or which we consider to be RF here, at any time, and from our chemical kinetics, you know that the rate is proportional to concentration of the reactant multiplied by the rate constant, which is what we have here. So for forward reaction, for that reaction, A plus B to give you, for that reversible reaction, A plus B to give you C plus D, then that means that the forward reaction is going to be K1 multiplied by concentration of A multiplied by concentration of B. Now, that is assuming that the rate constant for the forward reaction is K1. While the rate constant for the backward reaction is K2. We should have written it there, so please note that. It should be on those arrows. The top arrow, that is the backward reaction. The bottom arrow, that is the forward reaction. So we have K1 for forward reaction. But again, normally it should be drawn the opposite way. That is, the top arrow should be the one moving forward, while the bottom arrow should be the one moving backward. So now for that forward reaction, our rate of forward reaction is going to be equal to, from our chemical kinetics, is going to be equal to K1 multiplied by concentration of A multiplied by concentration of B, assuming that the order of reaction with respect to each of them is 1, 1. While for a backward reaction, you have your K2 multiplied by the concentration of C and concentration of D. You also know that because now that means that in this case of the backward reaction, your reactants now are going to be your C and your D. And now we already said that your rate of forward at equilibrium, remember what we said, that at equilibrium, the rate of forward reaction is going to be equal to the rate of backward reaction. We said that and that is why you have your RF is equal to your R, that should be RB, not RR, really. That should be RB, because if we write RF for forward reaction, we also want to write RB for backward reaction. So that second R, it should be RF is equal to RB. So now, of course, we can now bring back our complete formula for forward reaction and for backward reaction into that RF is equal to RB. So that will give us that next equation. Now, if you rearrange that equation, you want to make K1 divided by K2 the subject of the formula, then you will end up with that last equation that we have. And now K1 divided by K2, which is the rate of forward, which is the rate constant for forward reaction, divided by the rate constant for backward reaction, is equal to Kc, and that Kc, oh, sorry. Oh, gosh. Hold on, please. So that Kc Shouldn't be. Okay, so that case C now is what is known as the equilibrium constant. That is, your equilibrium constant is the ratio of the rate of forward reaction, or is the ratio of the rate constant for forward reaction to that of the backward reaction. And now, if you want to break that down according to what you have in that equation, then that means it's going to be the ratio of the concentration of the product. It gives the ratio of the concentration of the product of the concentrations of the reactant. Sorry, it gives the ratio of the product of the concentration of the product to that of the concentration of the reactant. This is not properly written, please. The constant Kc is known as the equilibrium constant of the particular reaction, and it gives the ratio of the product of the concentration of the reactant, of the concentration of the product to that of the product of the concentration of the reactant. We can revisit it again, so we can revisit that equation again. The last equation, you have your CCD divided by, the concentration of the product. You have two products, you have C as one of your products, you also have D as one of your products. Now, we're saying that your equilibrium constant is the ratio of the product of the concentration of the product. Because remember, product is multiplication. so divided by, or since we're using ratio, we can't use the divided by. So it's actually like your concentration of C multiplied by concentration of D divided by the product of the concentration of the reactant also. So that is your equilibrium constant. And it actually comes from this. It's as a result of law of mass action, which gives the rate as equal to or as directly proportional to concentration of your reactant multiplied by that constant of proportionality. You can look at it from the law of mass action. You can also write it coming from chemical kinetics. Now, the subscript C indicates that the equilibrium condition is expressed in terms of concentration terms, because you can have that equilibrium constant in a different form. But in this case, it's concentration. We're going to talk about the other form anyway. So in this case, it's concentration terms. So that's why it's written as Kc and not Kp. So you can also have it as Kp when it's actually coming as a result of pressure terms. So now, and in this case now, the subscript C indicates that the equilibrium condition is expressed in terms of the concentration units, that is mole per liter of various species. Now, if we consider a process involving more than a single molecule of each of the reactants and the products, then the rate is proportional to the concentration of the given substance raised to a power equal to the number of the mole of the substance. Now, this is where this particular line, that's the reason why, because normally this is the way I like to start. That is the reason why we don't talk about this. We don't talk about this too in terms of the kinetics, because if you talk about it in terms of kinetics or in terms of coming from the chemical kinetics, what we're saying now, that's why we're using the law of mass action. And that is why the rate is proportional to concentration of the reactant. When you want to introduce the constant of proportionality, you put your equality sign, then you have your constant of proportionality. Now, in this situation now, because the fact that you're dealing with equilibrium, you are assuming that it's an elementary reaction. You are assuming that you're dealing with an elementary reaction. And remember that for an elementary reaction, the order of reaction is the same thing as the molecularity. Meaning that in this case now, if you're having more than one or two, say A is equal to 2 molecules rather than 1, and that means you're going to raise your Ca to the power of 2. If so if your C is 3, then that means you're going to raise your C to the power of 3. So that is why we kind of like look at this, or we come at this from the angle of law of mass action. And that's why we're saying that you consider a process involving more than a single molecule of each of the reactants and the products, then the rate is proportional to the concentration of the given substance raised to a power equal to the number of the molecule of the substance participating. So that means for the reaction where you have a molecule of A, B molecule of B to give you C molecule of C and D molecule of D, your two rates are going to be equal to this. Now you're raising your A to the power of A, you're raising your B to the power of B, while you're also raising your C to the power of C and your D to the power of D. So your equilibrium constant now, or your general formula for equilibrium constant now is going to be this. That means that the number or the molecularity of that reaction has now been taken into consideration and it's now been added. It's now been added. So now, but again, you need to, if you look at this very well. Now, the last equation gives the most general definition of equilibrium constant. Now, by convention, you normally start from what you have on your right. That is, the equilibrium concentration of the substance appearing on the right-hand side of the chemical equations are always placed in the numerator. And the equilibrium constant expression and the constant of substance appearing on the left are placed in the denominator. That is by convention when you actually have an equation. But of course, remember, if we're saying that just like we use hydrogen and iodine to give hydrogen iodide as an example, and we're like, okay, the reaction can actually start either from hydrogen iodide or it can start from hydrogen and iodine. I'm talking about this equation now. That, okay, whether you're starting from here or you're starting from here. But of course, whichever one you're making your reactant or whichever one you're making your product is going to affect what your equilibrium constant is going to be. But there's a relationship between the two, because that means that one is just going to be a reciprocal of the other. Because one is just going to be a reciprocal of the other. If you're starting from C, if C and D are your product, or they're on your right-hand side, and you have this equation, if it gives you KC, then if you change that, and you're now making C and D your reactant, and A and B your product, then that means that if you want to rewrite this equation, you're going to have your CA and CB as the numerator, and your CC and CD as the denominator. In such a situation, you know that why the answers are going to be different, there's a relationship between the two. One is just a reciprocal of the other. And that's why you have K direct reaction. That is when you're moving from A, B to C, D. It's just going to be equal to, that is the equilibrium constant for direct reaction is going to be, it's just going to be equal to reciprocal of the equilibrium constant for the reverse reaction. Because at the end of the day, the only thing that is going to change is that you're just going to have your denominator and numerator swapping position. And what that means is that one is just a reciprocal of the other. Now, let's now look at this. So you have nitrogen and hydrogen are placed in an empty 5-liter container at 500 degrees Celsius. Now, when equilibrium is established, 3.0 mole so nitrogen, 2.10 mole hydrogen, and 0.565 mole. Please, I need to check that the YouTube is working well. I don't want, yeah, please, I want to quickly check. Okay. Okay, yeah, sorry about that. I needed to be sure that everybody there is also getting what we're doing. Now, okay, so some nitrogen and hydrogen are placed in an empty 5-liter container at 500 degrees Celsius, When equilibrium is established, 3.0 mole nitrogen and 2.10 mole hydrogen and 0.565 mole of ammonia are present. Evaluate Kc for the following reaction at 500 degrees Celsius. Of course, this is the reaction they're talking about. Now, you see the information you have here. These are equilibrium concentrations. That is, at equilibrium, you have 3.0 mole of nitrogen in 5-liter container. Because remember, you have a 5-liter container. So you have 3.0 mole nitrogen in 5-liter container, 2.10 mole in 5-liter container, then 0.565 mole of ammonia in 5-liter container. So while you were not given the concentration directly, you've been given the number of mole present in 5-liter. So essentially, you already have the equilibrium concentration given. So, but of course, you don't have it given directly. What you have is just the raw data for equilibrium concentration, meaning that you can calculate your equilibrium concentration. You can have your questions with the equilibrium concentration directly given. You can have situations where you have to calculate your equilibrium concentration yourself, like the situation we have here. So where you have to calculate your equilibrium concentration yourself. You were given a mole. Sometimes you can be given a mass. So now you have it in mole. Now you can calculate your equilibrium concentration. Of course, you will know that it's the number of mole per liter. And if this number of mole is per 5 liter, and you want to determine for 1 liter, all you need to do is divide by that 5. So and that gives you the equilibrium concentration. Now, you can now write your formula for Kc now, which is, remember, ammonia raised to power 2, because you have 2 mole of ammonia, and ammonia is the product here, divided by nitrogen raised to power 1, because there's 1 mole of nitrogen. You also have hydrogen raised to power 3, because there are 3 moles of hydrogen. Now, of course, you now substitute the value for equilibrium that you have. So that gives you 0.286. Now, what is the meaning of this when you see something like this? What does it really mean? Now, because there are 2 possibilities. You could have your Kc less than 1, it could be greater than 1. So, because that is just telling you to what side do you have that equilibrium. So the fact that, and again, remember that you have your product at the top, concentration of your product at the top, while that of your reactants is at the bottom, or the concentration of the product is the numerator, while the concentration of the reactants, they are the denominator. Now, what does that mean? Now, if you have that kind of arrangement less than 1, that means you have more reactants than product. That's what it means. So that means what you have as the denominator is greater than what you have as the numerator. And the implication of that is that the equilibrium is to the left. Because in this case now, you have 0.26, which is less than 1. It's only less than, it can only be less than 1 because the denominator is higher than the numerator. And that tells you that the equilibrium is towards the left. That is, you have more reactants in that reaction. You have more reactants in that reaction. But if it's more than 1, that could only mean one thing, that you have your product, concentration of your product higher than that of your reactant. And that means that you have your equilibriums towards the right. Now, for gaseous mixture, you rather than use concentration, of course, we use pressure, or the partial pressure exerted by each of those, because at the end of the day, that is also proportional to your concentration. Of course, it's also proportional to their relative concentration. Remember what we said. Oh, okay, sorry, that wasn't in this class. That was on that class. I was going to start saying that, of course, where the partial pressure of a gas is directly proportional to the mole fraction of that particular gas. Now, it's something similar here. Now, because each of these is actually going to be exerting pressure. Now, in an equilibrium mixture at 500 degrees Celsius, ammonia is that the pressure from ammonia is 0.147 atmosphere, nitrogen is 6.00 atmosphere, and hydrogen is 3.70 atmosphere. Now, remember, I said that rather than use, there are times when you use concentration, there are times when you use pressure. In this case now, what you're given is pressure, not concentration. And of course, you can do the same thing, and it's called Kp here because your terms are pressure, they are pressure parameters. Yeah, you're using your pressure parameters. So if you're using pressure parameters, then of course it's still the same thing. But the only thing is that what you're using here is pressure parameter. It's pressure parameter. Now, okay, there's something missing here. Okay, I do not want to. Okay, I think I'll find a way to come and resolve that. Okay, I'll come back to that. Okay, so now this is another one. This is another one. So consider reversible reaction of SO2 with O2 to form SO3 at 1500 Kelvin. And suppose you have 0.4 mole of SO2 and 0.20 mole of O2 are injected into a closed 1 liter container. When equilibrium is established, 0.056 mole SO3 was formed and 0.344 mole of SO2 and 1.72 mole O2 remains unreacted. Now, you want to calculate the equilibrium constant here. Sorry, I think when we were editing this slide for the new syllabus, I think we kind of like made also that mistake because the question should have actually ended with calculate the equilibrium constant. Now, in this case now, you look at what you have, 4 mole of SO2, 0.2 mole of O2 are injected. But when you establish the equilibrium, you have 0.056 O3 left. Now, that is the equilibrium concentration of SO3. But for equilibrium concentration of SO2 and O2, you are only told, 0.056 mole per liter now, because remember, you have a 1 liter container. So per liter, because that 0.056 mole is not the concentration itself, it's just the number of mole. But since you have it in 1 liter, because if this were to be 2 liter, that means you'll be dividing that by 2. But now, since it's 1 liter, that can be 0.056 mole per liter for SO3. But for SO2 and O2, what you're only given what was left. That is 0.344 mole of SO2 and 0.172 mole of O2 remain unreacted. Hold on. Yeah, it's still this. Okay, sorry, it's the same thing. So it's still the equilibrium concentration. I thought that they were saying that okay, that was what reacted. So that is still the equilibrium concentration. So what you have here are equilibrium concentration, because there are times when what you be given is just what to react. Somebody can just tell you that okay, say 0.152 SO2 reacted in the course of the reaction. Now they're now telling you to calculate what was left, because what you need is what was left, not what reacted. So now this is now what you have. The equilibrium concentration for SO2 is 0.344. For SO3 is 0.344. For O2 is 0.172, while for SO3 it is 0.056. And of course, you do the same thing. SO3, because you have 2 mole, SO2 you also have 2 mole, oxygen you have 1 mole, and of course that's going to be the final answer. Now, now I'm not sure. What did we do? You see, this slide should have come. I think when we were doing this, I'm not sure. So this slide should have come before this slide, because that was actually speaking to this slide. Because I thought I removed it completely. Well, I didn't mean to remove it, but when I saw that slide, I thought that I removed it completely. And now this is actually saying that for reaction involving gases, it is convenient to express concentration of any gas at any given temperature in terms of partial pressure, which was what you had on that. Now, to define equilibrium constant in terms of partial pressure of the reactant and product, then if you have this as your gaseous reactant and product, this is going to be your equilibrium constant. But now it's no longer Kc, it is now Kp. But now, sorry about this, because this is when you're trying to edit your notes to suit a new. Just a minute, please. I'm trying to see, because it seems I made a new slide. Now I'm asking myself why, because this, what I'm seeing here, I kind of like, I remember I saw it and corrected it. I'm trying to check what went wrong. Okay, sorry, please. Give me a minute. I need to check what's going on. So now I'm not comfortable with it. Okay, so I think we just need to. Okay. Okay, so okay, it's not, I corrected it. I didn't say that's what happened, because I chose to. Okay, so now remember, so we have two kind of equilibrium constants now. One that is actually pressure dependent or pressure determined, or one calculated from pressure parameters, while another one is actually calculated from concentration parameters. But of course, like I said earlier, when we first encountered this, I said, of course, you have a relationship between the two. There are relationships between the two. This took at any temperature, provided the gases in the reaction obey their ideal gas law. Now, since this is what you have for an ideal gas, the pressure is actually given by this for an ideal gas, where you have V as your volume occupied by N moles of gas at temperature T. But N divided by V is equal to molar concentration. We know this, the N divided by V, that's your molar concentration. Now, if you now have, because if we say that N divided by V is molar concentration, then it means that you can just come back there and substitute meaning you can rewrite this. That is, you have your molar concentration here, then multiplied by your, so you have your Kp, which is going to be your concentration, because the issue here is the relationship between your concentration term and your pressure term. And now all these are your concentration term. You write this as your normal equilibrium constant. It doesn't matter the number of products or the number of reactants you have. That's why you see the dot there. That all you're doing from here is that if my pressure is equal to concentration multiplied by gas constant multiplied by temperature, that means that all I need to do, if I want to convert my Kc, or if I want to convert my Kp, if I want to make my Kp from my Kc, is to add that concentration, is to add the RT, or is to multiply by the RT, which is what you have here. Because at the end of the day, everything you have here, this is your Kc. If you look at this very well, all these are your Kc, because you've introduced the concentration. You have your Kp, now you're bringing in the concentration. You're converting your concentration to pressure. So that is what you're doing here. Now, and that is why I didn't save because all those I kind of like wrote, I made 2 slides of this. So that means I didn't save it. Because I thought maybe I had it somewhere else. So now, if this was Kc, this would just be C raised to power C. Oh, sorry, C raised to power C, CD raised to power D, divided by CA raised to power A, multiplied by CB raised to power D. That is if we're dealing with Kc. But now we're dealing with Kp. And that is where the relationship between Kp and Kc matters. That means that if this is no longer our Kp, it's no longer our Kc, if it is now Kc, according to this now, that means we're going to have to multiply by RT. And again, so which is what you see going on here. But of course, we're still going to raise to that power anyway. So that is what you do here. You multiply this by this number, by RT raised to power C, multiply the other one, RT raised to that number of mole also. You do the same thing for the denominator. But again, you can rewrite this. You can rewrite this in this form. That is, you have your C raised to power C multiplied, because if you pull all this together, that means you can pull your RT term together. Your RT, that means you have your RT raised to power C multiplied by RT raised to power D. That means that is going to be your RT raised to power C plus D. That is going to be your RT raised to power C plus D. Then you do the same thing for denominator also. You pull the concentration term together and you pull your RT together. You are factorizing now. So when you also do that, you can also do the same thing. That means you are now going to just have your CA raised to power A, CB raised to power B, multiplied by RT raised to power A, multiplied by RT raised to power B. Now that RT raised to power A multiplied by RT raised to power B will now be equal to RT raised to power A plus B. Now your RT raised to power C plus D divided by RT raised to power A plus B can also be taken out, since both of them have RT term. So we can still deal with both of them together. So now that means, of course, that is going to be your RT raised to power C plus D minus A plus B. So that means that for Kp now, this is what you are. And if you look at it very well, the first term we have there is still your Kc. The first term we have is still your Kc. meaning that your Kp now can now be equal to your Kc, which is all this term you have here, that is your C raised to power C, D raised to power D, divided by A raised to power A, multiplied by B raised to power B, which is your Kc, which is what you have here, which is what you have your equation star. Now, so meaning that makes your Kc. Now, the only thing you have left is now going to be your RT raised to power, which is the change in the number of in the molecularity while moving from reactant to product. That's your delta N. Because if you look at this, you have your C plus D, which is the number of moles of your product, minus A plus B, which is the total number of moles of your reactant. And that's why we say change in molecularity moving from product to reactant. And that's your delta N. So now, where your delta N, okay, we have 8 minutes left. Okay, we'll have one more class anyway. So now, where your delta N is equal to the difference in the total number of moles of gaseous product and reactants during the reactions. Delta N can be 0, positive or negative. Where your delta N is 0, that is the number of moles of the reactant is equal to the number of mole of product, then what does that mean? That means that, of course, your Kp is going to be equal to your Kc, because RT raised to power 1 is going to be equal to, sorry, raised to power 0 is going to be equal to 1. And that means your Kp is going to be equal to your Kc. Now, this is an example dealing with that relationship. When delta N is negative, the number of molecules of the product are smaller. Of course, you know from where delta N is coming from. You're subtracting the number of molecules of reactants from that of the number of molecules of the product. So when delta N is negative, the number of molecules of the product are smaller than the number of molecules of the reactant. That means your Kp will be less than your Kc. Then, now let's now look at an example here. Let's look at the example. Now you have nitrogen plus hydrogen to give you ammonia. We've used this several times. Okay, I think I need this slide show. Now for dissociation of okay, what is going on? Oh, okay. Sorry, that's the question. I'm not sure how that got there, but we have a question for dissociation of water. H2O to give you H2 plus half O2 at 1,500 degrees Celsius. The value of Kp with partial pressure in atmosphere is 1.87 times 10 raised to power minus 6. Assuming ideal behavior of gases, calculate the corresponding value of Kc with concentration in mole per liter. Now, you already have your equation here. That is H2O to give you H2. Now, essentially, yeah, the number one thing is, okay, because this is your formula, Kp is equal to Kc multiplied by R to raised to power delta N. Now, the question is, what is our delta N here? Our product, you have 1.5 molecules of product, while you have 1 molecule of reactant, meaning that our delta N is going to be half. That is 1, which is the number of molecule of hydrogen, half number of molecule of oxygen, minus 1, which is number of molecule of hydrogen. Then our T must be converted to Kelvin. Then this is our R. Therefore, using this, you need to substitute all those into this. Then you're going to get your 1.55 times 10 raised to power minus 7 mole per liter. It's your Kc. Now, what are the properties of equilibrium constant? Hold on. Oh. What are the properties of equilibrium constant? Now, the equation for Kp and Kc are applicable to the systems which involve ideal gases. the following are some of the properties of the two equilibrium constants. Now, these expressions are only valid at equilibrium. We already said that. Because remember, before equilibrium, those concentrations of pressure are going to be changing. Before equilibrium, they're going to be changing. And of course, you can't talk about a constant at that particular point in time anyway, since they're still changing. So they're only applicable at equilibrium. And again, they have no relationship with the initial concentration of your reactant or product. As long as you're dealing with the same reaction at the same temperature, under the same condition, then it doesn't matter what you're starting with. It doesn't matter what those relative, whether you're starting with 0.5 mole of hydrogen or you're starting with, at the end of the day, that equilibrium concentration is going to remain. So that constant, that's why it's called a constant. It's the same. It doesn't matter what your initial concentration are. But they vary with temperature of the reaction. And of course, the equilibrium constant vary only with temperature of the reaction. And it's constant at constant temperature. And that's why, because if the rate constant vary with temperature, of course, the same thing will also expect something like that to apply here. So they change with temperature, but it doesn't matter what your concentrations are, or the initial concentrations are, sorry. Now, by knowing their value, we can determine the extent to which a particular reaction can take place under given condition. Large values of the constant imply that the formation of the product is large and the reaction is small on the right side. We already said that. That is, if you have anything less than 1, it means that, of course, you're going to have more reactant at the end of the reaction. If it is higher than 1, it means you're going to have more product at the end of the reaction. So, and that's the value tells you how much of a product you can actually form from a reaction. Now, it is also possible to predict quantitatively the effect of changing concentrations of reactant and product on the extent of a reaction. Now, if you have hydrogen and to give at constant temperature, Kp for this reaction is given by, as long as your temperature is not changing. But now, if you now change the temperature, now because we're talking about this reaction, you have this at constant temperature. But now, if you change the temperature, that is, you're disturbing, because when you change temperature, you're disturbing equilibrium. You're disturbing equilibrium, which is part of those things we're going to be talking about our next class. Because, okay, I think I need to stop here now so you can ask your question for the next 10 minutes. So we still have one more class, the class that I missed the last time. We're going to have to do that on Monday. So now I think we need to stop. I think I will start from here next class, so we can take our questions. Okay. Please raise up your hand for questions, because I don't like, I have the urge to rush and finish today, but that would be very, very unfair to you, really, because I missed last class. So, okay, we have very few slides, so yeah, okay, all right. So, Ian Joel, hold on. Before that, please, there's something that I need to, just give me a minute, please. But there's something that I keep. I'm trying to ask myself, what was it? Because I know that I wrote that down here, that I needed to quickly come back to it. I didn't talk about it because it wasn't, because, so that whatever it is, even if I'm not going to be able to talk about it today, I should tell you to remind me in next class. Oh, okay. So it's on unit for equilibrium constant now. Yeah, because I know that there was something that I said I wanted to talk about. I'm not sure. When we're editing that slide, we kind of like, I think I missed it. So please remind me, we need to talk about the units really before anything else next class. Okay, so because at the end of the, okay, I need to quickly, before you start asking your question, so that I'm not just going to get away from here without talking about it a little bit. So just give me a minute to quickly explain what I need to say on that. I don't know, did I remove all this units? Now, in terms of unit, the unit of equilibrium, the equilibrium constant, they have no fixed unit. Because at the end of the day, it's like, what is it called? It's like, I'm trying to, it's like your rate constant, it's like your rate constant also, which depends on the order of reaction itself. Because remember, at the end of the day, the order of reaction will tell you what the rate constant is actually going to be. It's also something, it's the same thing here. So because at the end of the day, you have concentrations and you can also raise those concentrations to a power, to a particular power. So in this situation now where you have all this concentration, remember, you're going to have mole per dm cube raised to power 2 here, mole per dm cube raised to power 1, mole per dm cube raised to power 3. At the end of the day, you need to cancel, you need to resolve all those to give you the unit. In this case now, that means you're going to have mole per dm cube raised to power 2 divided by mole per dm cube raised to power 4. That means this is going to be per mole, yeah, because that's going to be raised to power 2. That's going to be mole raised to power 2, per mole raised to power 2 dm cube, really, or per liter, really, or per liter raised to power 2. So now in this situation now, that means you're going to have something like, okay, I'm trying to write. Okay, maybe not now. I'll resolve that later. So at the end of the day, if you want to use your molar, you already know that this is molar raised to power 2 divided by molar raised to power 4. And that is molar, that means molar raised to power minus 2. That's going to be your unit here. And that means that's your mole raised to power minus 2, liter raised to power, liter raised to power 2. So that is how you, it's the same thing with pressure. At the end of the day, you have in atmosphere, you have all these in atmosphere. In this case now, this is atmosphere raised to power 2 divided by atmosphere raised to power 4. That means this is atmosphere raised to power minus 2. So I think one of the reasons why you had this there was the fact that I think we had those slides where we talk about the unit. We now use this as an example to introduce the unit, to talk about how we do the unit. But I'm not sure why I removed all those slides talking about the unit. So that's talking about units. So I can come back and take your question. Okay, the first person, Soma Ongwede, please unmute and ask your question, please.
Good morning, sir.
Morning.
Okay. Sir, in the question where we had to deal with unreacted concentration.
You're talking about this?
Yes, this question. Right. So why do we use the unreacted one as the equilibrium constant instead of the change due to reaction? I don't really understand that part.
Remember, that means you didn't understand. That means you didn't understand the concept itself. Now, you see, if you say equilibrium concentration, you're essentially talking about the reactant that didn't go into reaction. What is left? That's what you need. Remember, the one that has gone into reaction has gone into the reaction. This is not rate constant calculation. It is the rate constant calculation that you want to talk about the consumed concentration. In this case now, you are using what is left. You are using what is left. The whole idea is that the rate of forward reaction, the whole idea is that when a reaction starts, you have the rate of formation of the product. The rate of forward reaction is going to be decreasing why the rate of backward reaction is going to be increasing. They get to a particular point, they're going to be equal to each other. So in this case now, at equilibrium, what is left? That's what you want to know. What do you have in that reaction mixture at equilibrium? How much of SO3 do you have at equilibrium? How much of O2 do you have at equilibrium? How much of SO2 do you have at equilibrium? That's what you need. And if you consider that now, that means you're asking yourself, how much of unreacted SO2 do we have? How much of unreacted O2 do we have? Did that answer your question? Because that's a very important question for those who did not get it or who kind of like got something wrong there. Okay. I want to assume that I answered our question. That's why. Okay. Me she.
Okay. Good.
Yeah.
Good morning, sir. So my question is about the unit first for this KC. Like there is no unit there. If we actually meant to calculate it like in normal exam, are we meant to have a unit, and that will be like
wasn't that the last thing I said here? I said because I said the only reason why we left unit out of this calculation was because the original slide we spoke about unit after calculation. So we now use this because we kind of like did calculation separately on unit. How do you calculate the unit itself? So we did this, we didn't put the unit. We only said, okay, we'll talk about the unit later. But of course, you can't have them without, you can have equilibrium constant that has no unit. Because, but what we're saying is that their unit they don't have a fixed unit. Their units are dependent on what those concentration powers are. So, but of course, if the concentration of the denominator is equal to that of the numerator, then that means you won't have a unit. But in this situation now, there's a unit. But that's why it was the last thing I spoke about. I was already starting to take questions. I wanted to take questions before I came back to unit. So that means you were not paying attention.
Sorry, sir. And also, I want to ask that, like, in these reactions that we're using, it seems as if we are assuming that all of them are elementary, like as in we're using the actual molecular.
Essentially, yes. And I mentioned that they are treated as elementary reaction.
Okay, thank you very much, sir.
Yes. Next person, Tunde, unmute please and ask your question. Tunde. Okay, Ibukun Oluwa, please. Unmute, please. Ibukun Oluwa. Okay. Tunde, unmute. No. Ibukun Oluwa, unmute. No. Okay. I want to believe there are no questions again. So good morning, everyone. So I'll see you next class.
Hello, sir. Hello, sir.